All right. So we start in the morning. These are the formula that you can derive. The one that I did not mention in the morning is this: the fact that from the Minkowski tensor for a Gaussian isotropic field, we obtain identity matrix. It is independent of the threshold. And that is the signature of the fact that it's an isotropic. The covariance matrix that I input, it was for an isotropic field, and that has resulted in this. So it means it is one at all thresholds. So what I'm going to now in the next 2-3 slides, before we look at 21 centimeter application, is to go through all the morphology that we have defined. I just want you to have a feeling for what they look like. So the other, we have seen for Gaussian isotropic field, Minkowski functionals and contoured Minkowski tensor, we can derive analytically the beta, the shape statistic. So we have lots of structures. We can find beta for each one of them. You can average. Okay. That quantity, it is not possible. At least nobody has derived the analytic formula for it. So we have computed it for a simulation. This is for a Gaussian isotropic matter field. You can ignore all of this and just imagine that there is only one line. So for us, it's not important, the difference is coming. So the shape of the structures, so this on the left hand side are for the whole structures. And on the right hand side are the connected regions. Matter over density regions, this is telling us that they are typically in the universe and the distribution as this kind of a shape. So you look at the values, 0.6 around here. So 0.6 means it's quite elongated. So from a random distribution of structures that you obtain, the structures are always going to be elongated. Average behavior is given by this. So we saw in the previous results that for positive thresholds, there are a lot more connected regions, and for negative threshold, there are a lot more holes. Okay. So that's why the error bars are this. On the left hand side here for connected region, these are like typically one structure, very few structures. So that's why the values tend to be. So this is the behavior. And similarly so there is a symmetry between the positive threshold and negative threshold. For a Gaussian isotropic field, without any gravity acting on it, will show that the shape is identical from the positive threshold to negative threshold. It's symmetric. So if you combine all this information together, the total behavior, then we have this W shape. So what you can see from here is that the structures at high thresholds, they are few and they tend to become circular. That's why beta is tending to high values. And both void, think of this as void regions in density, both of them are. So I have unfortunately not included a slide for what happens to evolution after matter, after gravity affects. You start with this distribution at an early epoch and you let it evolve just by gravity from n-body simulations. You can find out what happens. So what happens is, what gravity does is, it makes these positive connected regions more and more circular. This you might have studied in some mass structure cosmology lectures, that you have heard of gravitational collapse, spherical collapse. That's a good approximation. Things tend to become, because gravity is a central force, it tends to become spherical. That's what we do see. If I compare at different times this plot, it will look like this will then go up. Later time we'll have a plot which is like this. Whereas the void regions, they become more. So from the void regions, what gravity does is pull out the matter and spin them towards high density regions. And that is a very asymmetric process, and we find that this is more asymmetric. The beta values drop on this side, but So this is this is an advantage. I mean, this is telling us how the evolution is affecting the matter distribution. Yeah. So this is for a Gaussian isotropic matter distribution. This is, for example, this is like we have taken large smoothing. So the small scale evolution, which is affected by gravity, is not affecting that. So it means a Gaussian isotropic field. The shapes of connected regions, high density regions, and low density regions are similar. That's what it means. So this is initial conditions to give this, and then you let it evolve, and the evolution will change, produce asymmetry. That is an effect of gravity. Does that answer your question? Oh, error bars. Oh, that's because there are fewer structures. So the error bars are, so at any threshold, you count the number of thresholds. That's a Betti number. You count the number of structures. And the error bar is you average and then find the standard deviation. So these error bars are there. So at this intermediate regions, we saw the previous experiment set example that there are a lot more structures are here. Experiment set consists of a lot more structures. Whereas at high positive and negative threshold, there are only a few. That's why error bars are larger on this. Okay, that's the B charts. Then let us, just to set the ideas, let's look at alpha. So this contains a lot of plot, but the overall shape. So we obtained this from simulations and Planck data. So the behavior of alpha is, so from the analytic calculation, I showed that the W102 should be a diagonal matrix, which is identity matrix. That means alpha should be 1. Eigenvalues are same, so it should be 1. But in real life, when we have a given data set, the alpha is going to average the alignment of certain number of structures. When we have large number of structures, you find that the probability that they will not be aligned, you will see the alpha tending to 1 is closer there, because there are a lot of structures. Whereas on this positive and low thresholds, there are just a few structures. So the probability that by random chance you just distribute structures, for a few, it is highly unlikely that you exactly put it in a nicely, isotropic manner. So that probability is very low. So that's why you have this value going away from 1. So, this alpha statistic was used to test statistical isotropy, and the purpose of my showing you here is not to go through the details of that, but just to show you the handy plot. You have lot of simulations of blue gray the data. Okay, so to complete the story now, I have not shown you Betti numbers. So Betti numbers, this is a calculation that I have. So they have this. So number of connected regions, it peaks here. Number of holes, it peaks on the negative threshold. And their difference is the Euler characteristic. So you can see they are equal and equal to 0. So the Euler characteristic will be 0 here. And this will flip and become the u e to the power minus 2. Okay, so is this point clear? So I have shown you all the things that I introduced, and I have shown you their calculation and how they behave as a function. Okay, so next, now that completes the introduction, and so we want to I want to give you one example of how we use this morphology to constrain 21 centimeter of so clearly, we have all been taught by fantastic lecturers and know much more than me. So you can catch me when. Okay, so we have the goal of the 21 centimeter interferometry is to get the 21 centimeter fluctuations, right? but you are measuring power spectrum directly, and finally to do tomography, the different chips you want to convert it from the power spectrum into images, and you want a volume of space, the data, the 21 centimeter emission from these different redshift slices, you want to construct that and have a full data set. So the this is like for SKA frequency range, 100 megahertz to 1 gigahertz. Then this will convert, because of the 21 centimeter redshift, it will convert into redshift of this range, okay, 30 to 0 on a very optimistic scale. But of course, starting with some maybe 10 or so is what we are going to start. So the image, the data that you get, you want to convert into image of fluctuations. And for me, for the applications of the morphology that I have described, we want this, and we want to apply the statistics on this. So that is the goal. At the moment, it's a very far off goal. We don't even have, I think in Hera's Hera paper, I saw Rob had given me one paper, the latest paper where they reconstruct a very small patch of the sky image, and it's extremely noisy. The pixel sizes are very large. So this is just the beginning. So this is what I am going to describe, this kind of futuristic, maybe next 10 years or so, hopefully we'll be able to do this. But anyway, we have to plan things in advance. Okay. So why are we going to do this? Because this will, the image that we want to use as the data will be direct observation of the various objects, and we want to do statistical inference. Okay, so the statistical inference, I already showed you 1 or 2 slides in the first lecture on how we do statistical inference, and that is what we are going to do. What I'm going to go here. So how do we do the statistical inference? Is the field 21 centimeter field is in Gaussian. I do have plot of the probability distribution, which is non-Gaussian. So we need to go beyond power spectrum to get the additional information. And of course, you might have seen papers which go beyond 2-point function. People like Somnath also, they have done 3-point function. There are papers which look at 4-point functions. So one can calculate the higher order moments term by term. However, it becomes very hard as you go to high endpoint functions. Computationally, it becomes very difficult, and so it is useful to think of an alternative, and that is the morphology statistics that I am going to talk about. Okay, so this is what we are going to do now. Okay, so let me present a flow chart of what we do. Okay, so this is like this picture is at different redshifts. There are dark regions are where the reionization has happened. Stars have formed, they have reionized the region, and we are not getting 21 centimeter signal anymore. And these are the regions where the signal is coming. So as redshift decreases, the regions become more and more reionized, and we are left with these small patches. So what can we do morphologically? We can count the number of ionized regions, bubbles. We can count, we can check their size. We can ask what is the shape of the ionized regions, what are the shape of the neutral regions. These are the kind of morphological questions we can ask. And for this, of course, the statistics that I described already, those are going to be. So these are basically morphological quantities. And for the physics side, we have studied the 21 centimeter modeling. So we want to know properties of sources, what are the times of sources, number of sources, how many stars are being formed in different epochs, and so on, location, how are they clustered. Then the underlying matter field, because the 21 centimeter is coming from hydrogen, and that is being coupled to the dark matter field, which is there everywhere. So there's the underlying density field that will also affect. So we want to infer all of this physics by looking at these images by doing mathematical analysis. So basically now, similarly, all of these different properties will affect the rate at which reionization progresses. And so we want to find that. So that is what. Okay, just to give you an idea of how in 21 centimeter study, how the morphological applications, there's a timeline of how people have applied. So I think maybe the first papers appeared around 2006 by these people, Glaser et al. So you can see they have been, so here they use, this one used Minkowski functionals. This one used only the Euler characteristic. And so whenever there is topology, it means there's only Euler characteristic, all of them. So there is also slowly over the years, there is slightly increasing because there's hope that we'll have data where we can apply this. Unfortunately, I collected this only till when I gave a talk. So there may be papers after this I have not checked properly. Okay, so so you can see all of the Betty numbers these people have used. Okay, so what I'm going to talk about is basically the work of my ex-PhD student Akanksha, and she has used these morphological statistics to do this forecasting. In some sense, forecasting the futuristic. Can we get constraints with this data? How we get the image? So I'm not an expert on that. So the image has to be provided by the 21 centimeter observing people. So they'll have to convert from data. So you get power spectrum, and from there you convert and get the image. So the mathematical inaccuracies and errors that enter into that process, that I'm not very well aware of. So we should ask somebody.
Many of these works include simulation.
This is going to be simulation, but from a practical point of view, this question is very necessary. How they are going to, maybe we can ask Saurabh after that. Okay, because for Hera they did it recently, and they gave one slice of where the image is reconstructed from the power spectrum. Which one?
This is
I'm yeah. I have one problem with Saurabh. Okay, so this is the what I'm going to describe to you. Okay, just to so whatever I'm going to talk about is only simulations, practical applications, practical issues. Most of it I will leave. Okay, so this is the expression for the 21 centimeter brightness temperature that we will use at different redshift and at different physical locations in space. So you are all well aware that it has a fluctuation field. The properties come from this ionized fraction, then the underlying matter density field, and the spin temperature. These are the three quantities which change from place to place, from location to location, and these properties are input into this. So this one comes from, we are going to use 21 centimeter simulations, 21 centimeter fast simulations of this work, that is what is used. And so they don't do full n-body simulation, they use approximation using Zelkovich approximation. And then the details of the reionization are input and three fields are one. Okay, so let us keep the cosmology fixed. That means I fix all the omega parameters and so on. All these parameters are kept. So cosmology is kept fixed and will vary only the reionization parameters. That also is a simplistic, simply a toy model. And so I am going to vary only two parameters. One parameter is the ionizing efficiency, basically the number of ionizing photons produced by stars that can vary from hydrogen to actually do the ionization. And so that is this. And the other parameter that I will be interested in is the TUV. So these two I want to wait and see. We will make simulations of this 21 centimeter brightness and we'll look at the snapshots of different redshifts, use them to calculate the morphological statistics. Create a mock data where simulation plus from the instrument what kind of noise is expected, we'll add it to that and we'll see whether we can recover the input parameters. Okay, so let's look at the morphology. First, I'll talk about the qualitative. Because before we do any constraining and so on, we have to understand how the physics gets encoded in the concept. Okay, so for doing this, basically, I'm going to define a size parameter. So let me go back to the, so n was supposed to be the holes and this everything is done in 2D. So n is the x, this small x here is the number of holes or number of connected regions. So x can be either hole or connected regions. So I am defining an effective size of the an effective size of the connected region structures or holes. And beta bar is also same thing. I am defining an effective shape parameter elongation for the connected regions, and so this averaging is all the shape parameters are being averaged over the number of or connected regions. So this shape and size information. So here is the plot of, let us understand this. So clearly this so this is the plot of the first one is showing number of holes, number of connected regions, the effective size of the connected regions, and shape parameters. So this is at different redshifts. So at different redshifts, clearly what if I look at this, so I'm basically looking at the number of different kinds of structures, then the effective size of the different structures, and the other one is the size and the shape, elongation of the structures. So these are the three information I am looking. And so you can see that there will be here maybe this is an early redshift when the stars are just about, some stars are just about formed. So you expect maybe for the whole region will be basically the ones which are like the ionized bubbles. Most of them will be high. Those you can see that there are more isotropic regions compared to here, and the number is more. Just isolated ionizing sources have come out, and their region around it is ionized, so they are more circular. And you can see that here. So as the ionized regions grow, some of them can merge. When they merge, the region becomes isotropy, or the beta parameter becomes more elongated. So that's what we see. And here again, towards the end of the reionization, only some isolated connected regions are left. And so the number of holes are very few, and they may be, the holes now may be left within this neutral regions. Maybe one star has popped out. There is this evolution that is happening that we can capture this muscle. Let's go back to that. Okay. So apart from what I described just now, you can also see the x-axis, the threshold range is dropping very much. Okay. So the nature of the fluctuation field, the range of values that it can take from negative to positive, this is mean subtracted, that is also changing. So most of it maybe it depends on the, so the redshift I'm showing is like 12 to 8.5. So here the range is like this. So there is a evolution in the range of the field values. Okay, so that this is the description. Now we want to condense the information, because how do I compare full size? Because I am dealing with different thresholds. good to condense the threshold information into one, and that is what I have done by integrating out in some threshold range of that I can compare these at different rates. There I just have a single number. So that is what this is. This is the integration. So this low and high, it is up to us. We played around with different values. Yeah. So that we can define. So here, this is a slice. So yeah. So usually you the two-dimensional slice from a three-dimensional volume. I'm just representing it in terms of the function. Z-axis, so xy is this plane, and z-axis is telling the field values, brightness, temperature values, field values. So how is it evolving? Let us see here. So early redshift is here. There are just a few stars. I'm calling it early, depends on your model. So let's assume that there are just a few stars or maybe galaxies have popped out and they have ionized the region around. So the value dropping here means that these regions are highly ionized. So these little drops which are coming, they are getting more and more ionized as the time passes. So at redshift 4, this is the level of ionization. And here at redshift 9, which is like, okay, half reionized, okay, there you will see equal distribution above and below. Whereas at low redshift, when most of them have become reionized, then the field values are here. And so there are only a few regions which are not. That is what it is. Yeah. Yeah, we had chosen some. For same slice for every redshift to do this comparison. You can do it for the cube, yes. You can do for all the slices. So this is our first, for example, work to demonstrate that this method. That's all. So I have not. Well, there's a lot of work to do. Z-axis is the field value, delta TB on a slice. So XY plane is this. Imagine it like this, and the field value, the color is showing the field value, delta TB value.
What is the red color?
So red color is very positive, negative.
When the field is positive, I'm saying that not an
Because this is mean subtracted. I have mean subtracted, that's why the value is changed. But on this range is basically ionized, and here means very little ionized. That is the value. That is the interpretation. So the expression set that we are using is different. The meaning of the expression, I think at the basic level, the expression set theory that we are talking about for defining the realized objects, the basic concept will be similar. But the way we are using is slightly different. So once that expression set formalism has been used to define the collapse objects and so on, then we get the field, and after that we are applying our morphology analysis, where we again do expression sets. We are completely different. Okay, is this picture clear? Yeah. This is so basically NX is Betty number at a threshold. So this is condensing. So when you have different thresholds, you have different Betty numbers. We have seen that. So this is to condense the information. Now, in the future, you don't have to do this. This way of doing it is throwing away information. You are averaging out. So maybe some physical effects will be strong at different thresholds, and we will lose. We will not lose, but wash out that information by doing this. But since this is the first study, and it's very hard to do the innovation and so on when you have different multiple parameters. For that reason, we have condensed the information by averaging out like this, integrating out the threshold information, and we used it. That is the only reason. So, in my lectures till the morning, we had done thresholding and we had found the threshold behavior. Now, for this study, we had condensed the threshold information, integrating out, and we use that and we see how they evolve as a function of H. Dimensionality reduction. Yeah, you can average. So you have this information here, different thresholds. I'm averaging out all that. That's why I say you will wash out something. This one. Oh, this integral. So in this thing, if I choose different redshifts, if I use different thresholds, like I choose a threshold here, I will say my number of hole is 1 because this is a hole. Okay, there are no connected regions. Then as you go up, you in this region you will say maybe my number of holes is 3, and so on. So it will vary from a particular threshold range to the particular. So now that information, instead of looking at each threshold, because it is hard to compare, how do you compare between one threshold and another? So we bring an integral over this. That is what we do. Because it is hard to define a characteristic, what is the best threshold value at which you should do your comparison. So that requires more study. You test out what are the various properties and so on. So instead of doing that, we just average out, and this integral is going from some threshold to this. All this information here is being condensed one number. Is that clear? Okay. Similarly, for the size and the beta, we are averaging it out. Okay, now that we have, for each of the statistics, we have condensed the threshold information, so we have one number for every redshift. Now we can look at different redshifts. As a function of redshift, we can plot and look how is it evolving, and we can connect with the physics that is happening. Okay, let's look at this one. This is not the full 21 centimeter field. This is the ionization X8. Okay, so let's look at the number. What does it say? It says that we are starting at around at early shift. There is a certain number of sources which have formed and which are doing the ionizing. So this is the connected region and hole. Let's look at the hole. Okay? So these are triangles. Let's look at this because this is the physically more interesting one in this region. So because I said that if a star pops up or a galaxy pops out and it ionizes, it is seen as a whole in my way of looking at the morphology. So what you are seeing here is that from very early redshift, the number is increasing. So that is, it is demonstrating that as more ionizing sources emerge, this number on the average number, even though I have averaged it, increases up to something. Then, so as more and more stars pop, that for the models that we are using, this is that redshift 14 or so. Then it reaches a maximum, then it is dropping. Now you can ask, why is it dropping? Yeah, it is dropping because mergers are starting. So as mergers start now, the count will go less, so it drops out. Yes. Yeah. That's why this is useful for picking out those time scales. Then the connected regions, which are the basically in this picture, the neutral regions. The neutral regions, you can see there are fewer because the entire thing, the entire region of observation will be one structure. It will be the beginning. And then they will increase. There's a period where the two of them are equal. Typically, we find that this happens at around halfway of reionization. And so then it comes. So this is how the number counts. The count is 3. Yeah, and sorry, this is an old plot, and so yeah, different colors are what? Oh, different colors. This. Oh, okay. The different colors are for different ranges of integration. So, yeah, this high and low. As you vary that, how does it? So, in this field picture, okay, this one, no? You're asking where is high and low. So that this for that plot we were studying how does it affect. If we vary this high and low, so basically it is from somewhere here, from very high, from 0 to very halfway. Okay? The threshold where halfway ends. So this is what we were varying to see how does it affect. It does affect, of course, because the range is going to affect. But yeah, half of it. So you can see, but the time scale information is retained. Mu 0 means the mean of the field. So it's not the plane, it will lie somewhere here. So for this field, mean 0 will be very close to the maximum because most of the fields are there, the field values are there. Here it will mean somewhere in the middle, and here it will mean somewhere close to the. Okay, any other questions? Okay, so we pick this out. You can see very nicely, even though when you vary, the scales don't change, but the absolute numbers change. So this is how the connected regions are behaving. They will be correlated with each other. Let's look at the size. So this is the size for whole connected region. So the whole region, again, this is to be expected. Yeah. Yeah, should be. I have not tried doing that. So, you talk to me later, maybe you can devise something. Yeah. So, what this plot is in this particular panel is that in the beginning, in the early redshift, the ionized region bubbles are small, and so you can see this value as more and more. Because this is an average quantity, it still remains small. And then when mergers start, you can see it increasing. So the sizes become larger as mergers happen. There is a mild increase here because ionization region of course is going, but it is not. It does not change drastically. It only changes drastically only when mergers start. So that is what we see. It will have a peak. Because then after that it will be the whole structure will fragment, everything will become ionized and only ionized bubbles will remain. Then on the shape information, this is interesting. So what you can see is that right from early redshifts, the shape is decreasing. That means it is getting more and more elongated. You may ask that even though these isolated regions are the isolated stars are coming out and ionizing, why is the shape decreasing at early redshift before 14? Because 14 is where we said, okay, the merger is taking over. So here you can ask why is it decreasing? And the reason for this is that in a region, so stars and so on will form in early epoch in high density regions. But they are clustered. So the peaks, there will be one big peak, and on top of that there will be mini peaks which are clustered together, and each ionizing source will form on top of these peaks, and they are close by. So the close by ones will start merging actually from quite early epochs, and that is what you are seeing. Okay? So then there will be an epoch where when you have mergers, when two mergers, okay, one circular, two merger, it becomes an isotrope. Wherever, if you have three mergers, okay, one here, and one here, you have seen that the shape that I explained to you earlier, if it becomes threefold symmetric, then it becomes isotropic again. So that is what you are seeing here. That when there are lots of mergers and lots of the bubbles are shaped in a very random way, in lots of perimeter, then it becomes circular. So the morphology is very nicely picked up by this. And similarly, you can look at these are for connected regions. The connected regions are less interesting for the EOR, at least in these early epochs, because everything is one connected region. Only when it starts fragmenting sub regions, then it picks up. So number picks up, becomes isotropic. Okay, so this is a qualitative finding for the morphology. Then now that we have the data, you can also do a distribution in size and beta probability distributions. So this is for the ionization field, and this is for the brightness temperature field. So the ionization field, you have all studied that ionization field dominates over the brightness temperature, is the main contributor towards lower redshift, right? So that is what we wanted to compare between the early redshift and. So these plots are different redshifts, blue, cyan, and red. So how the distribution of the this is for R, this is the size distribution, and this is the shape distribution. So the size, of course, it goes over, let's look at the range first. The range will be in various megaparsecs. We have done smoothing to the field, so it will be cut off by the smoothing on the inside, the low size sites. So this is the kind of distribution that we. Then for the shape, the shape quantity beta is a value which lies between 0 and 1. And so this can be approximated by a beta distribution, and it has this shape. So we can infer this distribution of bubble size and shape. So in the literature, I have seen that people model this by log normal. There are some work where they model the distribution of bubbles when one is trying to do theoretical estimation. Good to know how the bubble sizes are distributed. It is usually, I think, at least to the best of my knowledge, I've seen this model as log normal. So maybe it is close to log normal. Okay, shall I move on from here? All right. So that is the qualitative understanding. So now what do we want to do? What we want to do is, our goal is constraining EOR parameters. So that means that all this behavior that we are seeing here, this is for one model. Now if you vary say zeta, ionizing efficiency, or TVDL, these plots will change. Okay? And the question is, do they change? How far do they change? And when we have data, by comparing this plot, we'll obtain these plots from the data. We'll obtain these plots from theory for a wide range of values, and by doing a visit, then we find out which is the one that find out the model that agrees. That is what we do always in cosmology. For most of the cosmological analysis, that's what we do. So that's what we do. But of course, we don't have data. So we don't have data, and so we want to create a mock data to prepare for SKA. Here is the pipeline. So I'm not showing the sensitivity to model parameters. It will just be repetition of the plots. So we did another study and we found that they are sensitive to model parameters. And so now we can. What is the analysis pipeline? So the pipeline is we construct mock observed data for some fiducial model. That means I fix my cosmology, I fix zeta, I fix TV real, and I make a simulation. That is going to be my mock observed. Then to that we will add instrument noise. So for that we choose SKA instrument noise. And so we will obtain the morphological statistics and we'll say, okay, that is going to be my observation. Then we'll make simulations, various simulations for different parameter values. And we will see how in the parameter space, how it works. Then we'll do a Bayesian inference to do this. Okay. The mock data has these values. Theta is 17.5, TVDL is this much. And then for the Bayesian inference, we need priors on zeta and TVDL, so we have chosen this. Then this is the simulation. 400 megaparsec box and resolution is 0.5 megaparsec. Okay. So we need to have some understanding of the, maybe you have got the idea of how it is done, so I can skip this. Okay. So to add to the simulation, we add instrumental noise for SKA low. You have know more about this than me. We simulate the image and we add instrument noise for the different parameters. The noise, various factors that enter into the noise. Okay. So these are the different values that we have chosen for this study. And right now, our analysis is done only with one redshift. We did this for different redshift is going to add much more. So one redshift, which is 7.5. Why did we choose this? We chose this because, okay, so just to give an idea of how the noise affects. So this is a simulation without any noise at 7.5 redshift. Smoothing is 4.5 megahertz per parsec. Then the noise, added noise with observing time 100 hours. See that the overlying is small scale fluctuations which enter into the field. Then if you do 2000 hours, then the noise is decreased. So you can see, visually you can see. Now if you do, because smoothing also removes the noise. So between this, the study of which is better, what should you do? So the simulation, the smoothing, if you do 6.5, larger smoothing and so, then again the small scale. Then these plots are a comparison of the effect of noise for different smoothing. Same lecture. So you can see that the parameters. So this on the x-axis are the smoothing scales. So at the smoothing scales which are poor, like lower than 4.5, you can see that noise is adding extra bias to the statistics. So both the number counts and the size, shape, so on, they are affected. So there is an optimum. So it's better to higher smoothing scale, do the analysis with higher smoothing scale. At higher smoothing scale, you lose information. Okay, so finally we come to the constraints. So like I said, this was our first study. We have not continued after this. What we obtain is, the first one is to see whether we recover input parameters from Bayesian inference. These dots are the input parameters. So you can see there is slight bias in the statistics. The recovered best fit values are with 1 sigma away. and so on. Theta and TVDL. Okay. I forget now why mean xi is also. Let's look at OG. So this is the plot with noise. Faintly with noise, the recovery is better. Don't ask me, I don't understand why this happened. But the size, the error regions are larger as expected because there is a lot of noise in the data. So this is the recovery. Properly weighted. Okay, so I think this is my last slide for this one. So what I have done now is to give you an idea of how we use a morphological statistics to constrain parameters. Okay. So we have applied it to this, but this method can be applied to, for CMB, it is not very competitive because the power spectrum is much better. But for 21 centimeter and classical structure, which are highly non-Gaussian, these kind of statistics, they add a lot more information compared to using just the power spectrum. So you should not think of it as a competing methodology, but you should think of it as we have the power spectrum, and then we need all these extra things, extra statistics, which can provide additional information, and we want to combine all of them together to extract as much information as possible. So that's how we should do it. So this is about constraining parameters. So the other applications are yes. This uses MCMC. I didn't stress on that. That is just how you sample the parameters. That is not the crucial thing. Yeah. So this is for use. For this we use MCMC. Yeah. How is it related to bispectrum? Yeah. Okay. So they are related as it. So this I think maybe in the tutorial you will see more action. Okay? So it is related because these morphological statistics are averaging over the space, the entire field and their derivatives. So they are basically encoding the integrals of the bispectrum, trispectrum, and all higher order endpoint functions. They are integrated and they enter into the functionals or whatever is the morphology. And how does it enter? If for tomorrow I will hopefully look at non-Gaussian fields. So if for a non-Gaussian field general, you don't know what it is, some non-Gaussian, it's different from Gaussian. Then you can calculate the Minkowski functionals, and it will not have that Gaussian shape that I showed today's first lecture. It will deviate. That deviation will depend on whether there is 3-point function, whether there is 4-point function, and higher order. Now you can ask, if it is only 3-point function, what does the shape look like? If it is only 4-point function, what is the shape look like? Okay, they will be different. And so by looking at the shape, you can distinguish. So also it complements the endpoint function way of extracting information. You can do 3-point function, calculate 3-point function directly and extract, or you can do this. You can do this kind of morphology and extract the information, and this should be similar. They change very much. That's the point. We know what to expect for a Gaussian field. Analytic formula is there. For a mildly non-Gaussian field also, there is some formula which Matsubara has derived. Now that's the point. All these statistics will differ. So here We did not worry about Gaussianity or non-Gaussianity. We did parameter inference. But the other application is that if a field is non, then these morphological behaviors will be different. And by looking at the difference, how much different is it from Gaussian? By looking at that, you can tell what is the nature of the non-Gaussian.
What there are two fields. One is Gaussian, one is non.
Yeah.
Same with the pole.
Yeah.
Can we tell the two is Gaussian?
Yes, by looking at the shape. Same number means amplitude will be same. Okay? When I plot the Euler characteristic, for example, they may have the same amplitude, but the shape will be different. If it is Gaussian, it will have this nu e to the power minus mu square by 2, shape is fixed. But if it is non-Gaussian, then this shape will be distorted. It will be nu e to the power nu square by 2, maybe I pull it out, then I put an integral 1 plus some new functional, new dependence will arise. And that will tell whether the field is Gaussian. So that is another, yes.
So for the Gaussian to create conversion,
Yeah.
in the way that you did.
Yeah.
So let's say we have a slide and see the waves and everything. How will you actually calculate that these are the number of poles and connected regions? Actually from that.
From the data.
From it.
Okay. So I explained that in the morning. That I was showing there are two ways of calculating. So I look at the data and I will actually look at the data and connect my pixels. Same iso field lines, I will try to draw the boundary and find the external set. Then from there you can count the number of poles and so. That's one way of doing it. That's a very labor intensive way. The calculation is harder. The other way, where I don't actually count individual structures, but I calculate for the entire field by doing field derivatives. That is the process I described. Okay. So the answer to your question is yes, you have to develop the algorithm, and there are algorithms which are developed and which can be used to do that. You look at the field values, define your expression sets, and you can count. Yes. Yes. Yeah. Yeah, we made it. Yes.
That is a great model.
Yes.
In that case, we play with the we will do the bicycle first.
Yeah.
Which
So
one is better?
the answer to that question depends on the kind of non-Gaussianity present in the field. So, for example, if the field, the non-Gaussianity is of bispectrum type, means you can write it as like something like an FNL, truncate your perturbation expansion there, and the other terms are small, then bispectrum is okay, you will directly measure. But if the non-Gaussianity is such that the bispectrum is small, FNL term maybe there is some symmetry which will say that okay, 3-point function is 0. Okay, then the next leading order term will be 4-point function. And if you are using bispectrum to constrain your non-Gaussianity, then you are going to get 0. So you will not see. So when a priori, when you don't know what the nature of the field, as a first step, and you have access to good image, then I will say the best method is to first study do with morphology. Yes, it's giving everything.
But it needs the picture.
Yes.
That is hard.
Yeah, but that is for 21 centimeters. But for example, what Fazlu is going to show for like the Haslam data, because there we have very good there the finding is in Fazlu's first paper is people have been looked at the bispectrum for it. They found that okay, bispectrum is not safe. So what we found is that actually bispectrum is not large, but it is not because of the mix of vertices. So that was a surprise finding, and this demonstrates that okay, it is important to look at these, using these different.
When you say that you're checking the part of you're checking whether there are higher correlations present. You can also infer that from this. Things will be given if there is a 2-point correlation, or either if there is a 3-point correlation.
I didn't fully understand your question.
If
So 2-point
this
correlation,
question,
he asked something?
when you are answering this question,
Yeah.
that the 2-point correlation functions or 3-point correlation, will be changing the amplitude of the.
Oh, the shape.
Yes.
Yes.
So from that, I can also tell you that if there are higher correlation functions.
Yes, you can tell, yes. Because this is like an agnostic method. See, it's an agnostic method because you just look at the data, calculate this, and you calculate sigma 0, sigma 1. That gives you your analytic expectation for Gaussian form. Subtract the two and you get some shape. And that shape, you don't know a priori what it is. So that shape will capture higher correlations, but in comparison, if you're using bispectrum, you will get 0 if there is no bispectrum, or if there is no next leading order to the usual perturbation theory present, then you will not see. So that is why this shape as a function of mu, that tells about the nature of non-Gaussian. So I think I was explaining about the shape that will inform. There's nothing wrong. Yes.
So maybe it fix a scale.
Yeah.
And then get the cost of information from the shape and the elevation. From the shape, we can this method. We can also get the cost of
It is possible to relate. Yes. Yes. So for that, I need to show you some formula, which hopefully I will show tomorrow. So you need to see the formula for this morphological statistics for non-Gaussian field, but mild non-Gaussian. Strong non-Gaussianity, there is no formula.
maybe suppose it's a complete Gaussian.
Yeah.
And then I have the method to confirm the new sequence.
Yeah.
What
What if it is Gaussian? Yes, you can. Yes. Yeah. Yeah.
But this is the real space.
Yes.
Usually we can get to the correlation.
Well, you can do Fourier transform and get the power spectrum. Though it is going this way and then this way.
First check if someone gets an image.
Yeah.
Estimate the power spectrum.
So we do it routinely. So hopefully will you show some power spectrum going back and forth. Of course, PMB it is done routinely. For Haslam map, he done that also quite a lot. But 21 centimeter, like I said, these 3 papers are the only work that we have done to be report here. So a lot more things to be studied. This was only the yeah, it will. I can give you estimate of this, but I cannot give you estimate of using bispectrum. Maybe one of you can work with someone. So this is computationally expensive, but with maybe 1 or 2 parameters, it is doable within days. Because we are using 21 centimeter file. But if you use a really more realistic simulation, then it yeah. Yes. Okay, shall we pause here and then we'll continue after the break?